Okay, so today we are going to do the final parts of time series. And I specifically chose stock prediction or stock forecasting data set in order to allow you to see to appreciate the differences between the models we learned last week, or rather the models we learned earlier this week, and the models that we're going to learn today. So let me do a quick recap of what we learned last week. So last week we learned about the different types of time series forecasting model. We have the autoregressive model, we have the moving average model, we have a combination of those two called ARMA, and then we have another variation of ARMA, which is called ARIMA, which handles the differencing. And we say differencing is a way of doing what? Why do we difference our data? Very good. Changing non-stationary to stationary data. Why is it important? Why is it important that we change non-stationary time series data to stationary time series? Pardon? Yes. So the underlying assumption behind these models is that your data is already stationary, and therefore you have to make, if it is non-stationary, you have to make it stationary. So we went through ways of making it stationary. We talked about differencing. What is differencing in a nutshell, like as you've understood it?
The differencing is always indicate small projects one share. In fact, it subtracts the development of yesterday's tomorrow.
So one of the methods of making non-stationary data stationary was differencing. We also have log transformations, and we say log transformations is used especially in cases where your data is highly seasonal, or you can also use seasonal differencing. And then we did a stock price forecasting practical, right? And this is what we came up with. At the end of all our processes of checking for stationarity, decomposing our time series data into the three components. What are those three components? We said a time series is made up of three things. That is trend, and seasonality. Yes, exactly. So after we decomposed, after we checked for stationarity, after we removed our stationarity, we plotted our ACF and PSCF. We did auto ARIMA, which I said is a library that makes time series forecasting easy for you. You can think of it as kind of like hyperparameter tuning. The way it works is kind of like grid search CV or random search CV, because you feed it options for the different orders, so different orders of P, Q, and D, and it figures out the best performing model so that you don't have to read the ACF and PSCF plots, because those can be subject to human error. But always plot your ACF and PSCF as tools to validate also the auto-ARIMA. So we did our auto-ARIMA, and we looked and we did our forecasting, and we came up with a forecast that looks like that. And this means, right, so we have the training data, which is in lighter blue. We have the test data, which is in that deep, rich blue. And then we have the predicted value. And we saw when we use our ARIMA, it predicts a straight line. And this straight line means it predicts a constant mean. And then we have this confidence interval, this confidence band, right? And this confidence band basically means the confidence that this value, or the confidence that the stock price is at this value, it increases as time goes by, right? But where is the value? The value is at the mean. So what is happening when you fit auto arima to things like stock price data? What happens is it defaults to the mean. And the reason why it's defaulting to the mean is because stock price data is very, very volatile. Today, Trump can wake up, say something careless, and the stock plummets. It's not like temperature. Whether Trump say wakes up angry or not, December ya last year ni December kama ya ile ingine. We always know January is going to be hot. We always know it's going to rain in April. Hi. It's so noisy.
It's noisy in here today.
Yeah.
Maybe it's because of this. I just need to notice how much sound just leads sound reduction.
Yeah.
Because yesterday when Kai and you guys are talking, I was in a meeting, it can't talk.
You could hear us.
Yeah, very loudly.
Wow.
So it's
And I didn't know it would be a big deal. I genuinely thought it would be three people. Yeah, it's a huge production team. They've taken three.
we should have a plan.
When was that supposed to happen?
Planning.
Yeah.
I think it's like an accounting thing, like money. So you get some money from this space.
You can do that. Yeah. Yeah. Tunafanya heteroskedasticity.
B2B stuff there.
All right. So the reason why it defaults to the mean, right, is because it's highly volatile. Stock prices do not act like typical time series data, right? Even when you have even ice cream sales are quite seasonal, right? Unless there's it's very high. Ice cream sales can sort of be predicted. You expect that people will be consuming ice cream when it is hot. Or if there's a spike, maybe a spike on Valentine's Day where, ice cream is used as a whatever. But when it comes to highly volatile data, we call this data heteroskedastic, right? Do not worry about the name. Skedasticity is like a Greek word meaning dispersion. So you can think of heteroskedasticity meaning your data has a high variance. And it makes sense. Stock data varies. It can open at 100 and close at 5 in less than 12 hours. It can close at 5 and shoot to, that's why Elon Musk today, this week, I think he was announced as the first dollar trillionaire. But you'll find, give it a year, he'll be back to his billions, right? And it's because of how stocks operate. They are highly volatile. And because of that high volatility, which is called in very statistical, technical terms, it's called heteroskedasticity. When it comes to stock prices, we do not, instead of predicting the stock value itself, we make the assumption of, okay, how about I predict instead the volatility? And the assumption behind the models we're going to be talking about today, which is GARCH and GARCH, the key assumption is this. It says it is based on an assumption called clustered volatility. And clustered volatility means this. If yesterday's price was highly volatile, even tomorrow's price is going to be highly volatile. So these models of GARCH and GARCH, instead of modeling the actual price, you see, when we were doing ARIMA and auto ARIMA, we were attempting to predict the price value. So GARCH comes back and says the price value itself is highly volatile, which makes it very complex to model. Right? Remember, when you, in mathematical terms, when I say coming up with a model, it's coming up with a mathematical representation of a process or a mathematical representation of a phenomena. It's very difficult to model actual stock prices. So GARCH and GARCH, they come and say, okay, When I look at stock prices, any day that the price is highly volatile is also followed by a day where the price is also highly volatile. Any day that the prices zinashuka is also followed by a day that prices zinashuka. Therefore, let me model the volatility instead. So that's what it assumes. It assumes that it shifts from modeling the raw value itself to instead modeling the volatility. And it comes from this concept called volatility clustering, which is what I've just explained. In stock prices, ikianza kupanda, inapanda. Ikianza kushuka, inashuka. Ifanyangi hivi, right? It doesn't go up and down, up and down, up and down. That would be randomness. But when the stock price, when the markets are good, if today the price was 100, it will just keep on being 101, 100. So, or if, let me not say, let me move away from the price. If the volatility today is high, if the markets are bad today, the markets will be bad tomorrow. If the markets are good today, the markets will be good tomorrow. So it attempts to model that natural phenomena of volatility clustering. So that's the essence of ARC and GARCH. Don't even go into the specifics of the mathematics. It's quite hardcore calculus. This guy won a Nobel Prize because of this model. What I want you to appreciate is that shift your mind from forecasting the raw values to now we are forecasting volatility. And why is it useful? Why does it make sense in the financial sector to be modeling volatility instead? The use case here is when you are doing an ARC and GARCH, or even if you're doing stock forecasting, you're not interested in knowing if Safaricom is going to sell at 100 or 99. It's impossible to know that. But you're interested in knowing, should I sell or should I not? How can I manage my risk? So when it comes to this particular domain of, it's called quant finance. When it comes to this particular domain where you're handling highly volatile data, it's about managing risk as opposed to predicting actual value. It's about modeling volatility. If you run this model through your data and you find that your data is highly volatile, the markets are highly volatile, don't sell, don't buy. If you find that the volatility is low, go, sell, buy, whatever stock people do. Okay, so that's pretty much it. So I'm going to show you an example. We're going to run through the same data set, the same stock prices, and we're going to see how it does a much, much better job of modeling stock prices when we shift our focus away from predicting the raw prices to predicting volatility. So here we go. You will install the special library called ARC, right? So pip install ARC. I have my models there, my library is there. I'm reading the stock data. I am changing the date to date time. Make sure anytime you're doing any time series forecasting, your index has to be the date. Yeah. So the date column is not an ordinary column. The date column needs to be indexed because that's how, when you're feeding input to your ARMA, SARIMA, ARC, GARCH, that assumption has already been made. And I'm going to keep it simple. I'm still going to be forecasting for one. Now, in time series forecasting, you have two types of forecasting. You have univariate forecasting, which is what we have been doing, and what you'd pretty much be doing, where you only forecast one. If I'm forecasting ice cream sales, my data set looks like date ice cream sales. There is multivariate forecasting where I am forecasting inventory needs. So I have the date, the ice cream sales, the weather, that's multivariate. Okay. And their deep learning does a better job at multivariate than these basic models. Here is my time series. It had some trend, and here is data preprocessing. Now, the data preprocessing for ARC and GARCH is a little bit different from our ARIMA and AutoARIMA. And it's because in ARC and GARCH, you are modeling the change in return, right? You're modeling the change in return, like you're modeling the returns. So for example, you are modeling what is the, remember volatility is how volatile the prices are. So volatility will be difference between price ya jana na price ya leo. That's volatility. That difference is what we are trying to model. That's what we are defining as volatility. So let's understand a couple of assumptions of the ARC and GARCH models before we do anything further. So the next step makes more sense for you. So in ARC and GARCH, we use returns instead of prices because prices are non-stationary, right? You've seen in our original data, it's trending upwards or downwards. And the fundamental, just like in ARMA and AutoARIMA, the fundamental assumption of majority of time series data is that your data is stationary. So returns, on the other hand, are stationary. So the percent change from day to day has consistent properties throughout time, regardless of the price level. Additionally, returns are scale-free and comparable across different stocks and time period. So when you say I'm a 5% return, it means the same thing whether it is you're dealing with a stock of 10% of $10 or a stock of 1,000. So it makes communication very easy. You can communicate across the entire finance. So if I tell you the stock you've invested in Safaricom, you are looking to gain 5% out of that, you can easily do the computations. And it's also easy to do error analysis. So if I say we've missed the mark by 5%, you can do 5% of 10,000, 5% of 100, depending on how much you've invested, right? Whereas raw prices are not. So if I tell you that the model has predicted that you're going to get 10 shillings, it's very hard to translate that. Or rather, let me say, that is actually a standard that is set by the domain experts. The guy who came up with this is what we call a quant finance guy. There's a whole domain in finance called quant finance. Those are the guys who are employed in BlackRock, employed in these big hedge funds, and their job is just to run the numbers, right? So most importantly, GARCH models volatility. Volatility is the rate of change, the degree of change. It doesn't model the price levels. And returns, it captures these changes properly, right? So if you tried to fit this ARC or GARCH on raw prices, the model would fail because prices follow a random walk. Prices can be basically random walk just means prices are volatile, all right? So the first pre-processing steps when it comes to ARC and GARCH is either you have two options. Either calculate the returns, which is more or less differencing, right? Or do the log of returns. Because anytime, just like in logistic regression, anything in the log scale becomes more stable. So it's very easy to model statistically. Remember, when we say model, is you are translating a phenomena and communicating it mathematically. And in mathematics, we talk of something called like stability, statistical stability, which just means if I put X times Priska, it should always give me the same answer, which we call deterministic, right? Deterministic just means if I say 1 plus 1, it's always going to give me 2. When we transform things to log transforms, we give those values an upper hand statistically. We make them more statistically stable, which makes it easy to model, which makes it easy to translate them mathematically. There is absolutely an option. You do not have to do log of returns. It's just that log of returns is faster, better. Even computationally, it will take less time. Okay, so here I do my log of returns. I drop, remember when you do differencing, you kind of drop you create like a a null value at the top, because that first value doesn't have something to be minused from. I get, right? And then I multiply by 100 just to make it easy to interpret, so that I have things like 5%. So I can say things like 5% change, 2% change, even. And then, as you can see, what have I done? We have made our very non-stationary data, and by translating them into log of returns, we have made them stationary. And that was the essence. Raw values are not stationary, but if I do log of returns, it becomes stationary. And we said stationary data has a constant mean, and it has a mean and variance that is not affected by time. And it typically looks like random noise, just like you see there. Right? Now, can you identify any conditional clustering? So we've said in ARC and GARCH, or in heteroskedasticity, the main assumption or the underlying mathematics that led to these models is that it argues that the volatility today, the same volatility today will be the same volatility tomorrow. So periods of high volatility follows periods of high volatility follow periods of high volatility. Periods of low volatility follow periods of low volatility. So you end up with things called volatility clustering, because the high volatility periods zitakuwa pamoja, the low volatility periods zitakuwa pamoja. And you can see that even in the random noise. There are some periods like here. Like here was a period of high volatility, zinaambatana. Then there's a period of low volatility, zinafuatana, which makes sense. Like the markets are they kind of are pretty usually very less volatile unless Trump does something, Xi Jinping does something, Russia is bombing sijui who, right? So when the Strait of Hormuz is going through terrorists, volatility shoots up, and that volatility maintains, and then when that issue subsides, the markets balance. And then Trump says gay people should be like hung or something. The markets shoot up, it goes, it maintains that period of high volatility, and then it goes back and everything. And that's just how the markets kind of swing. All right. And you can't do that with the raw prices. Now, after you have made your non-stationary data stationary, the other thing is we say you have to test for ARC or GARCH effects. And the essence of this is just to see, remember, in ARC and GARCH, you're assuming that your data is following this phenomenon called conditional clustering. Right? So that when we say you're testing for ARC effects, you are testing for conditional clustering. So if your data doesn't have conditional clustering, ARC and GARCH are not the best. Okay, so make your data stationary, test for ARC and GARCH. So the core idea is to check if the variance or the errors are correlated with past values. What is conditional clustering, Priska? So tumesema conditional clustering ni periods of high volatility are followed by periods of high volatility. So in essence, you can kind of say, if I know the volatility of yesterday, I can calculate the volatility of today because I am in a cluster, right? So if I know the volatility of last week, I can calculate the volatility of today because they are correlated with each other. Right? So while you can see volatility in the plot above, we still need to statistically test to determine if we need ARC and GARCH model. And this is what we call testing for the ARC effects. And the core idea is to check if the variance of the errors is correlated with past values. And that's just checking if your time series data actually has conditional clustering. Ask questions. Ask a question. You good? Okay. So a simple and effective way to do that is to see if the squared returns. So in our case, we're going to do the squared of log returns. So you'll do the squared returns if when you are changing from non-stationary to stationary data, you used the return. So you just did a simple differencing. Or in our case, we did the log return. So we're going to square the log returns and you're going to check if the square of the log returns are autocorrelated. All right, so we're basically doing an ACF of the squared log returns. And if they're correlated, it means periods of high volatility follow periods of high volatility. Periods of low volatility follow periods of low volatility. And as you can see the correlation. All of this data are correlated with each other because you can see the lollipops are above the what did we call that blue band? Because we have a name for it. Yes, I did. We call it the confidence interval band. And what does it mean?
So, I think basically I'm simply out in the.
Go for it.
Okay. So if any point that is above the confidence interval that is too high, for example, when you are dealing with the other the air and all that, can be able to know how many steps or the number.
Hello. Hi. We have class here, but not the whole day. You need this room? From our side or from your side? Okay. You're about to start shooting right now. We could move. We could move. Like align our schedules much better. This can totally be done. To the front. Hey, man, kuna kamera, kuna yo.
didn't know it was that serious, man. Umepigiwa kelele mpango kucheza.
Hata wao wanasema tunawapigia sherehe.
Pole.
Who is that?
Me. You want to sit there? You can another task stress. Stress.
Too stressful. I bite my nails instead.
You feel like saying that in front of
A student.
people.
I see what you mean.
Really. What do I do? What is it?
She's making money, man.
She's making
Money.
money.
That's a whole team.
Yeah.
Plus food. It's a whole team.
Also, that's a good plan. Maybe it's online, not in employment. So that's
Yeah.
a better promotion.
But there's some people who like really crack their employment. So it will be noisy. But okay. We proceed? Yes, unless I share again. How about now? The internet is really bad this week, but even the internet at home is really bad.
Yeah, everyone is complaining.
Still, and it was okay before.
That's internet.
Mm.
I can export it.
Let's see if once we reload if it changes. Okay, good. So we said the underlying assumption GARCH is making is called what? The underlying assumption is called conditional clustering, which is
So that's an assumption.
yes. And then you built a model around an assumption, right? So you have to test if that assumption has been met so that you know if you can actually apply this model or not. So the assumption of conditional clustering means the volatility today is dependent on the volatility in the past. So periods, it's clustering because periods of high volatility follows periods of high volatility and periods of low volatility follow periods of low volatility. That's all you need to understand about GARCH. That concept of conditional clustering, right? Based on this issue of heteroscedasticity, which we said is
Okay, we give it negative.
Priska, you know I ask questions.
Yeah.
Heteroscedasticity is, we said hetero is changing, scedasticity is dispersion of variance. So highly volatile data. That's pretty much what heteroscedasticity is. And because of that heteroscedasticity, this guy called Engel comes up with this concept of conditional clustering and builds a model around that concept. Heteroscedasticity means high data with high variance, which means it's volatile, right? And this volatility is, instead of us forecasting the raw prices, let's model the volatility. How are we able to model the volatility? It's based on this concept of conditional clustering. Periods of high volatility are followed by periods of high volatility, and therefore you can predict today's volatility based on yesterday's volatility. So that's pretty much, but you don't even need to go into the complex math. Understand those, what's heteroscedasticity and the concept of conditional clustering. Okay, so that's what we're testing for. We're testing for the arc effects. And because we've said that the key assumption here is today's volatility can be modeled from past volatility, we do an autocorrelation plot of the volatility, which is our log of returns, right? So there is, we do an ACF of our squared returns. Remember, sisi tumefanya log of returns. You have the option of doing returns. We have done log of returns because logarithm gives more stable. Statistically, logarithms are more stable than raw values. So you'll do an ACF plot of the squared log of returns. And as you can see there, what does an ACF plot tell us? It tells us what? Temporal dependence. So this tells us this is, remember, x-axis me, day 0, day 5, day 10, day 15, day 20, day 25, day 30. So you can see the volatility can be, it's the volatility 30 days back, right? All of them are statistically significant because the lollipop plots are above the confidence interval, the confidence band. And you can see how it goes. As you can see, you can think of that clustering volatility almost, I don't want to say seasonality, but I know when I say seasonality, it's going to kind of click for you in a way. But you can see how it goes. There's a pattern to it. And therefore, this pattern is what we are modeling. So when you see this, right, when you see this, gosh, what have I opened here? Okay, I don't know what I've opened. When you see this, it means there's temporal dependence in your volatility, in your log of returns, which means you can therefore confidently apply your arc and GARCH. So that's what we mean by testing for arc effects. Okay? All right? So that's how. The other non-visual way of doing it is you calculate this objective metric called the Langbox test. Right? And the hypothesis is that there's no correlation in the squared returns, so there's no arc effects present, and the alternative hypothesis is that. So if the p-value from the Langbox test is less than 0.5, you can confidently use your arc models. So you don't have to understand null and alternative hypothesis, just understand how to interpret the p-value. Right?
When it is less than 0.5 is
you can do there's no temporal dependence, right? If it is less than 0.5, there is temporal dependence, and therefore you can use the arc.
together.
The names are different, but the interpretation of the p-value is the same.
Okay.
The other one was called, we called it the
Yes, I remember this, the other one.
ilikuwa inaitwa augmented
Yeah, augmented decay for something.
Dickey Fuller.
Yeah.
There you go. The interpretation of the p-value is the same. If it is less than 0.05, you reject the null hypothesis, and therefore your data is non-stationary.
Yeah.
Go through the notebook. The notebook, I don't know if you ever read the notebooks I share with you guys. I write it in my own words.
What I get, I like that.
Okay, perfect. Okay, so we're going to do this Langbox test, and that's how you do it. And here you go. The Langbox test, it gives us the p-value at specific time lags. Right? So here I've tested it until time lag 10. Right? So at time lag 1, it is 6 to the power exponential negative 65. So that's 0.000000000 all the way to 65, right? So as you can see, all the way to lag 10, all of them are less than 0.05. And therefore this ARC effects all the way to 10. You can absolutely check all the way to 50 and you could see what that gives you. But this is a telltale sign that our data has ARC effects and therefore we can proceed applying ARC or GARCH. Ask a question.
The trick is again.
So we've said the key, the importance here is we're checking for the p-value, right? And we're checking specifically if the p-value is less than 0.05. So if our p-value is less than 0.05, it means we have ARC effects. So there's conditional clustering, and therefore we can apply ARC or GARCH. Iko sawa? All right. Now that we've confirmed ARC effects, we can now go ahead and start fitting our ARC and GARCH models. Remember, time series train test split si ya scikit-learn. Train test split is you have to maintain the temporal nature on both sides. Okay. So it's the past predicting the future. Okay. And there you go. I have my log returns, my train data set, and my test data set. Let's go ahead and fit a simple arch. Okay. All right. So there's something I did not explain. So there's this, what's it called? There's this, you can think of it as the model order, right? So there's this parameter Q, which is the order of the ARC model. Remember, we've said the volatility, what are we modeling when it comes to ARC and GARCH? The assumption is today's volatility is based on the past, the volatility of the past. So we still have the same question as with every time series model, which is how far in the past do I need to go, right? And the parameter that gives you how far in the past you need to go is that parameter Q, and that's what we're feeding here. Or rather, it's the parameter P. Q is when you're fitting GARCH. Now, ARCH is the baseline model, and then GARCH is there's GARCH, there's eGARCH, there's so many variations of it, but this is how the object you create, right? The object meaning the model, the ARCH object you're going to make will have these variables, right? You feed it the train data, you say what model you are feeding it, which is the ARC model. You give the order of the ARC model, which is P is equals to 1. And then Q is only used when you have GARCH, when you're applying a variation of ARCH. Sawa? And there you go. Give us a summary, and then it gives us a report like that. What did we say? What did we say is the importance of looking at standard residuals? And how should our standard residuals look like?
So
Our standardized residuals.
they should have no pattern.
Exactly. And what does it mean when it has patterns?
That means
It hasn't captured that temporal dependence. It hasn't learned that temporal dependence properly. Good. The second graph is just conditional volatility. It's just showing you, and it just, you see, what does it mean? Period of high volatility follows, you see, we said it's conditional. Yes. Where is the clustering? So you can identify places of clustering. Here is a low cluster, here is a high cluster, high cluster, high cluster. That's pretty much it. So this time, instead of fitting just an arch, I go ahead and fit a GARCH. And the only parameter I'm changing is I'm including a parameter Q. And there's my GARCH. And I can see GARCH kind of does a better job of modeling the conditional volatility. As you can see, doesn't this kind of almost look like our stock prices compared to this? Yeah, this doesn't really capture that daily nuance, and this does, right? Okay, How do we test time series model? Like, what's the evaluation metric we use for time series models? AIC and AIC, yeah, which is information criteria. Okay, so here I'm just checking the information criteria for both, and then now I apply. This is what my model has given as the conditional volatility. Remember, we are modeling what? Volatility. We're not modeling raw prices. Okay. Another thing we said that, remember when we did our ARMA, there are 4 diagnostic graphs we plotted. It was the standardized residuals, a histogram, a correlogram, and the one with the fancy name, QQ plot. Okay. The guests need it, it's fine. You can. I feel like how your mother akubalingi uchukue the fancy plates for a game. Yeah, so this is pretty much what I'm doing. I am checking what is the standardized residuals for the ARC model. Remember we said in BIC and AIC, the higher the better. So it looks like, yes, let's confirm. Let me confirm. Yeah, you're right. So it's lower. Yeah. So we should have gone with ARC and GARCH. They give better BIC and AIC scores. All right. But the process will be the same. So after you establish which model performs better using the AIC and BIC, you go ahead with what's it called? You go ahead and do like a diagnostic check of that model. And the diagnostic check includes plotting the conditional volatility, right? And seeing if you actually can see that conditional clustering. Of course, plotting the standardized residuals. The standardized residuals shouldn't have, plotting a histogram of the residuals, they should have a normal distribution. That's just an assumption that's made when these models are being built. Your QQ plot should not have, we call them pigtails, right? These blue lines should be, these blue scatter plot dots should be along the red regression plot as much as possible. Right? So you've plotted your QQ plots of the standardized residuals. No, it's not. And you see, it kind of has this tailing at the very end. And it could be maybe it's because I did GARCH instead of, I did ARC instead of the GARCH. Let's see. Yeah, I fitted the arch instead of fitting the GARCH. Let me see. No, I fitted the GARCH, right? So that would mean we'd probably need to play around with the order of the GARCH, right? Remember here, my order of my GARCH is only 111, which means I'm only going one day in the past. Maybe the volatility for stock prices should be a good place to start is maybe 5, because the markets, they run on like a weekly cadence, or maybe even 30 days in the past, a whole month, right? So those are now the things you see, but look at that. Standardized residuals are perfect. They look good. But yeah, the QQ plot is a telltale sign that I need to change the order. They should be as close to the line. I don't know if you saw the QQ plot for the ARIMA, it was almost really perfect. But I want you to learn that when you're doing the diagnostics, you think of it collectively. So you just don't say QQ plot imeharibu yoyote. It's grounds for investigation, but not complete like dismissal. Okay. So the next step would probably be changing the order of my models and see if that improves the QQ plot. All right. Okay, and then here, describe residuals. And then here, this is, you don't need to do this. And then here I do, now I'm forecasting the volatility. So I've finished my training and modeling. Now I'm moving to forecast my volatility. And why do I forecast with ARC? Should have forecast with GARCH. And let me show you how. See, when I forecast with GARCH, it's able to capture. Let me see. Much better than ARIMA that was giving us a straight line. And there you go. And then you just calculate your mean absolute error. So here my mean absolute error is I am probably off by 0.79. Actually, it's 0.79%, because we already did the times 100 up there. Yeah, 0.79%. That's how good my model was. Any question? Please follow the notebook.
It does not estimate. I got it.
Now, any questions for the topics we've covered so far from clustering? Have you done your week 2?
Already started.
Why?
I had the issues of two different places.
Yeah. Has that been sorted?
Yeah, it has been sorted.
Mhm.
So I still have that you gave out for the week 3. So I want to go and try and see if I'll do all of them one weekend. Hopefully.
I gave out
Yeah, you mentioned that.
that.
We do week 3.
Yeah, you can totally do week 3 even without ARC and GARCH. Yeah, you can totally. Week 3 is air quality. Should be straightforward. Any questions on all the other topics? Let me
Those
stop
that
the
you've
record.
covered so far.
Anything that's not making sense?